Hello, and welcome to this quiet space, sleepy science quest. Tonight, we invite you to set aside the worries of the day and let the noise of the world fade away. This channel is a sanctuary for slow, peaceful storytelling, a place where the narration moves like a gentle stream, designed to help you unwind, relax, and perhaps drift into a deep, restorative sleep. In this episode titled, Why You Can't Change the Past, we will step into the silent, echoing halls of a laboratory where the very fabric of reality is under examination. We will follow two brilliant minds as they stand on the edge of the known universe, peering into the riddles of black holes, wormholes, and the stubborn, beautiful nature of time itself. It is a journey through the laws of physics, exploring the boundaries of what is possible. So, find a comfortable position, take a deep, slow breath, and close your eyes. Let your mind wander to the stars as we begin. Elara stood in the center of the Kronos laboratory, the low hum of the quantum supercomputer vibrating through the soles of her shoes. The room was dark, illuminated only by the holographic projection floating in the air before her. It was not a complex equation or a map of the stars that occupied her attention at this moment, but a simple, humorous poem from a magazine dated December 19th, 1923. The green letters hovered in the cool air. There was a young lady named Bright who traveled much faster than light. She started one day in the relative way and returned on the previous night. Professor Aris, Elara said, her voice echoing slightly in the large metallic room. It always comes back to Miss Bright, doesn't it? The dream of moving faster than light to undo the mistakes of yesterday. Professor Aris, a man whose hair was as white as the chalk he preferred to use on his blackboards, stepped out of the shadows. He adjusted his glasses and looked up at the floating poem. Indeed, Elara. But for a long time, that poem was just a joke. Physics said no. The speed of light was the ultimate speed limit. To break it was to break reality, or so we thought. Elara swiped her hand through the air, dismissing the poem. In its place, she summoned a new simulation. A wireframe cylinder appeared, glowing blue. It began to spin. We started taking it seriously in 1937, Elara recited, reviewing the history that formed the foundation of her thesis. W. J. Van Stockham. He was a Scottish scientist who published a paper that nobody paid attention to at first. And why is that? Aris asked, testing her. Because the math was too clean, Elara replied. Van Stockham used Einstein's general theory of relativity. He predicted that if you had a massive cylinder and you spun it, space itself would get dragged along with it. If an observer went into orbit around this spinning cylinder, and if the cylinder spun fast enough, the observer could return to her starting point before she even left. On the hologram, a tiny red dot, representing a spaceship, moved around the spinning blue cylinder. The dot left a trail that looped back on itself, closing a circle not just in space, but in time. A closed loop, Aris nodded. Precisely. But the problem? The problem was the cylinder had to be infinitely long, Elara said with a sigh. It's impossible to build something that goes on forever. So, people ignored it. They said general relativity didn't explicitly forbid time travel, but nature made it impossible to build the machine. It was a mathematical trick, nothing more. She waved her hand again. the cylinder vanished, replaced by a swirling image of galaxies, a model of the entire cosmos. Then came the 1940s, she continued. Kurt Gödel, the famous logician. A friend of Einstein, Aris added. They used to walk home together at Princeton. Right. Gödel found a new solution to Einstein's equations. He discovered that if the entire universe were rotating, everything would change. In a spinning universe, a spaceship could spiral away from Earth and find a path that led back into its own past. You could go anywhere and any when you liked. Elara manipulated the hologram, showing the universe twisting like a great cosmic whirlpool. It proved that time travel was theoretically possible within the laws of physics. It disturbed Einstein greatly. He had worried about backwards time travel ever since he first wrote down his theory of relativity. Gödel showed him that his fears were well-founded. But we do not live in Gödel's universe, Aris pointed out softly. No, Elara agreed. It was just a model, a curiosity. Astronomers in the 1940s knew galaxies spin, but the universe as a whole, no. Today, we are certain. We have measured the heat radiation left over from the Big Bang. It's uniform. There is no cosmic rotation. Gödel's machine was the universe itself, and the universe refused to cooperate. Elara walked around the console, her mind working through the mechanics. But the secret remains, Professor. The secret is rotation. That is the key that opens the gateway. Explain, Aris commanded gently. It's about the speed of light, Elara said. We know the rule. Nothing travels faster than light. If you could mess up cause and effect. You could change before and after. You could break the timeline. But rotation is a loophole. She brought up a new image, a dense, heavy ball spinning rapidly in a mesh of grid lines representing space. General relativity says a massive body, like a black hole or a dense cylinder, acts like a vortex, she explained, tracing the twisted lines on the grid. It drags space and light around with it. Usually this effect is tiny. Earth drags space a little bit as it spins, but not enough to notice. But if the object is heavy enough and spins fast enough, it twists the gravitational field into a whirlpool. Light itself gets caught. And the astronaut? Aris asked. The astronaut is the swimmer in the whirlpool, Elara said. She enters the field. She is dragged around. Locally, looking at her own speedometer, she is moving slower than light. She isn't breaking any laws of physics in her immediate vicinity. But because the space she is traveling in is being ripped around the circle, she completes the circuit faster than light would travel in normal, flat space. Locally, she is slow. Globally, she is faster than light. She achieves Miss Bright status, relative to a distant observer. Frank Tipler, Aris muttered. The 1970s. Yes, Tipler proposed a superdense cylinder spinning at half the speed of light. A finite cylinder this time, not an infinite one. It would work as a time machine, but again, not physically realistic. The forces would be too great. The forces would be too great. The density required is impossible to construct. Elara leaned back against the console. the blue light of the hologram reflecting in her eyes. Rotation is the old way, Professor. It's brute force. It requires energy and materials we can't engineer. We need a shortcut. We don't need to spin the universe. We need to sculpt it. You are talking about wormholes, Aris said. Yes, the modern idea of a time machine. No spinning cylinders. Just a bridge, a tunnel from point A to point B. Ilara brought her hands together, and the hologram shifted. The spinning ball flattened out into a sheet, and then the sheet folded, a tube connecting two distant points. By traveling through the wormhole, an astronaut goes from A to B before light can get there the long way around. If you beat light, you beat time. But to understand the wormhole, Aris said, walking towards the large viewing window of the lab that looked out over the university grounds, you must first master the black hole. You cannot run before you can walk, Ilara. I know, she replied. The black hole is the father of the wormhole. Ilara cleared the simulation and brought up a star, a massive, burning sun. How to make a black hole, she began, shifting her tone to that of a lecturer. It starts with a star, not a small one like our sun. Our sun is modest. When it dies, it will become a white dwarf. But a giant star, that is a different story. She watched the holographic star on the screen. It was red and angry. When a giant star burns out, it runs out of fuel, she said. It can no longer push out against the crushing weight of its own gravity. It collapses. It falls in on itself. If it's big enough, it becomes a neutron star. But if it is truly massive, nothing can stop the collapse. Not rock, not metal, not neutrons. On the screen, the star imploded. It happened in a flash. One moment a giant sun, the next a dark void. Our galaxy is peppered with them, Ilara said, her voice dropping to a whisper. The dead remnants of giants born billions of years ago. And at the center of the Milky Way, there is a monster, a supermassive black hole, 1,000,000 times the mass of our sun. Some galaxies have ones 1,000 times bigger than that. They eat gas and stars, spewing out jets of radiation. Why black hole? John Wheeler coined the term in the late 1960s. Ilara answered. It describes two things perfectly: blackness and emptiness. Let's start with emptiness. When the star collapses, the core implodes in a fraction of a second. It leaves behind a region of empty space, hence the hole. And the matter? That is the mystery, Ilara said. Imagine the star is a perfect sphere. As it shrinks, gravity gets stronger. The surface pulls in. Because it is a perfect sphere, everything falls toward the exact center. The ball gets smaller, gravity gets higher, and the shrinking speeds up. It is a runaway train. Where does it stop? It doesn't, Ilara said. Under the laws of relativity, it ends with the entire contents of the star concentrated at a single point, a dot. Infinite density, infinite gravity. Mathematicians call it a singularity. It is a place where math breaks down, an alarm signal that something drastic is happening, but the gravity remains. The star is gone, but its ghost remains, haunting that region of space with a ferocious pull. That is the hole, a footprint of gravity left by a star that has vanished into a single point. Elara paused, looking at the black sphere on her screen. That covers the emptiness, but the blackness, that is where time comes into play. Elara tapped a key on the console, and the holographic sphere in the center of the room shifted. The dark void remained, but now faint grid lines appeared around it, bending and twisting as they approached the center. "The stronger the gravity, the bigger the time warp," she said, her voice steady. "This is the second property, the blackness. It isn't just about paint or lack of light. It is about the death of time." She pointed to the edge of the collapsing star on the display. "Think about what happens to time at the surface of the ball as it contracts. The gravity is immense. Relativity tells us that gravity slows time down. As the radius gets smaller, the slowdown factor rises. When the ball shrinks to a critical radius about 3 kilometers for a star the size of our Sun, the time warp becomes infinite. Infinite, Aris repeated, testing the weight of the word. "Meaning time stops." "Exactly. The march of time at the surface grinds to a total halt relative to us, sitting here on Earth. If you could place a clock on the surface of that collapsing star, it would appear to us to be frozen in total immobility." "But no clock could survive that," Aris noted. "True, but light is a clock," Elara countered. "Light waves oscillate like a pendulum. As the time warp escalates, it retards those oscillations. The frequency drops. Lower frequency means the color shifts. The light from the contracting ball gets redder and redder. It fades like the dying embers of a cooling fire. Eventually, the frequency drops so low that the light just stops. It vanishes. After that, all is black. The region is black and empty. A black hole." She brought up 2 figures on the simulation, labeling them Sally and Sam. Sally was positioned far away, safe on a station like Earth. Sam was standing right on the surface of the doomed star. "This is where it gets strange," Elara said, watching the simulation play out. To Sally, watching from Earth, the star's collapse seems to slow down as it gets redder. In fact, for a normal star, the fade-out happens in a few hundredths of a millisecond. But technically, the final image of the star freezes just before it crosses that critical line. Sally sees the star collapse to a black ball and freeze there forever. She never sees it truly finish. And? Aris asked, looking at the tiny figure riding the star down into oblivion. "Sam experiences something infinitely different," Elara replied. "Remember, time is relative. There is no slowdown for him because he is inside the gravity well. He doesn't see himself freeze. He sees the star shrink to nothing in the twinkling of an eye. As far as Sam is concerned, in the fraction of a second it takes him to cross that critical horizon, all of eternity passes by in the outside universe." She swiped her hand, and the simulation reset. It creates a terrifying conclusion, Professor. A black hole is a one-way journey to nowhere. You cannot fall in and come out again, because the region inside is beyond the end of time relative to the outside. If you did manage to pop out, you would have to come out before you fell in. You would be projected back in time. Aris paced slowly around the console. So, the black hole has an entrance, but no exit. It is a fast track to the end of time, not very useful for a traveler who wants to return home for dinner. No, Elara agreed. But it provides a clue. What if there was something like a black hole, but with an exit as well as an entrance? A tunnel instead of a pit? A wormhole, Aris said. Precisely. Maybe it could be used to reach the past. But to understand a wormhole, we have to stop thinking of space as a fixed stage where things happen. We have to understand that space is elastic. Elara cleared the black hole simulation. The room was bathed in a soft, neutral light as she brought up a simple grid. It looked like a sheet of graph paper floating in the air. Gravity affects space just as it affects time, she explained. Relativity demands that space can stretch. We see this in the expansion of the universe. Galaxies move apart because the space between them is stretching. But because space has 3 dimensions, it can do more than just stretch or shrink. It can curve. Curved space, Aris mused. It sounds like a contradiction. Only because we were raised on Euclid, Elara said. She drew a triangle on the flat holographic sheet. At school, we learned that the 3 angles of a triangle add up to 180 degrees. That is the rule for flat surfaces, like blackboards or exercise books. She tapped the air, and the flat sheet morphed into a globe representing the Earth. But look here, she continued, drawing a new triangle on the sphere. Start at the North Pole. Draw a line down to the equator. Turn 90 degrees and go along the equator. Then turn 90 degrees again and go back to the North Pole. You have a triangle with 3 right angles. That's 270 degrees. On a curved surface, Euclid's rules don't apply. Navigators know this. You can't use flat maps for long journeys without accounting for the curve. And this applies to empty space? Yes, Elara said, replacing the globe with a glowing model of the sun. If space is warped, the rules change. Imagine drawing a huge flat triangle around the sun. Relativistic theory predicts the angles would add up to a little bit more than 180 degrees. Why? Because the sun's mass curves the space around it. Protected person. She gestured to the light beams passing near the sun. We usually say, gravity bends light. But it is more accurate to say that space itself is bent, and light is just following the straightest possible path through that curved geometry, like a marble rolling in a bowl. The effect is small for a star like the sun, Aris noted. Barely discernible, Elara admitted. A few seconds of arc. But we can measure it. We observe light rays or radar signals passing close to the sun, and the delay proves the curve is real. But for a time machine, we need a much bigger space warp. A massive gravitational field. To zoomed out, showing a galaxy. Sometimes an entire galaxy acts as a lens. It lines up in front of another galaxy, and its gravity bends the light from behind it, creating a halo called an Einstein ring. That's a huge warp, but the most spectacular warp is near our old friend, the black hole. The black hole returned to the display, looking like a deep funnel in the fabric of space. At the surface of a black hole, gravity is billions of times stronger than at the sun, Ilara said. Space is spectacularly warped. We can picture it like a rubber sheet. She gestured to the grid again. It lay flat, then dipped in the middle where a heavy ball represented the sun. A small ball rolled across this sheet, curves around the pit, just like Earth orbits the sun. But replace the sun with a black hole. The rubber sheet in the hologram distorted violently. It didn't just dip, it plunged downward into an apparently bottomless funnel. It curves away dramatically, Ilara whispered, staring at the depth of the gravity well. A pit with no bottom, or perhaps it ends in a singularity, an edge of space-time where the math stops. Quote, Ludwig Flamm studied this geometry in 1960, Aris added, long before the term black hole even existed. He did, Ilara said. But in 1935, Einstein and Nathan Rosen took another look. They found something strange about the shape. They discovered that the funnel didn't have to end in a point. She manipulated the hologram, the bottom of the deep funnel. Instead of pinching off into a sharp tip, opened up again. It flared out, connecting to a second sheet of space underneath the first one. The Einstein-Rosen bridge, Ilara announced. Today, we call it a wormhole. The narrow bit in the middle is the throat. Far from the hole, space is flat. As you approach, it falls into the pit, but then it opens into a second surface. Another universe, Aris said, his eyes twinkling. That is the best way to describe it, Ilara replied. The bottom sheet represents another universe, or perhaps a distant part of our own, folded back. But this model, it has a fatal flaw. The flaw is that it is a trap, Ilara said, her voice echoing slightly in the quiet lab. She adjusted the controls, and the holographic wormhole began to pulse. The Einstein-Rosen bridge is a beautiful mathematical idea, but it assumes a static universe. It assumes the wormhole just sits there, open and waiting. But in reality, this structure is dynamic. It changes with time. She watched the throat of the wormhole on the screen. Initially, the two universes, the top sheet and the bottom sheet, are detached. Then they connect at a single point. This is the singularity, where space curvature is infinite. From this singular beginning, the throat opens out. It widens, looking like a tunnel, but this only lasts for a fleeting moment. On the display, the tunnel snapped shut as quickly as it had opened, leaving the two sheets disconnected once again. It pinches off, Aris observed, nodding slowly. Like a soap bubble bursting. Exactly, Ilara said. The sequence happens so fast that nothing can get through. Not a spaceship, not a radio signal, not even a single particle of light. If an astronaut were brave or foolish enough to jump into the black hole hoping to traverse the wormhole, she wouldn't make it across to the other universe. She would enter the hole, but before she could cross the bridge, the throat would pinch tight. She would end up hitting the singularity at the center and being totally obliterated. So, Aris mused, the Schwarzschild wormhole is a bridge that collapses the moment you try to step on it. It creates an other universe that is purely hypothetical because it can never be visited or seen. It's worse than that, Elara added. This model assumes empty space. It comes from Karl Schwarzschild's solution for the gravity outside a star. But stars aren't empty. They have interiors. If you try to patch the math of the star's interior to the math of the exterior, the whole bottom half of the wormhole disappears. The other universe is deleted from the equation. So, unless the universe was born with these wormholes already embedded in it by nature, they won't form naturally from collapsing stars. And even if they did, they are impassable. She swiped the failed wormhole away. The room returned to darkness for a moment. "We need a better way to look at this," Aris said, stepping closer to the center of the room. "You are describing space and time as if they are separate players in this drama. But to solve the riddle of the wormhole, you must treat them as one. You must look at the fabric itself." Space-time, Elara stated. "Show me," Aris commanded. Elara brought up a new diagram. It was simpler than the swirling black holes. It looked like a graph. A vertical line crossed a horizontal line. "This is not hard to envisage," Elara began, tracing the vertical axis. "In this diagram, time is drawn vertically, and space is drawn horizontally. For simplicity, I am showing only one dimension of space left and right. The white lines on the graph represent the paths of physical objects moving through history." She drew a straight vertical line, labeled Path 1. Path 1 represents a body that remains at rest, she explained. It isn't moving left or right in space. It is only moving forward in time. As the seconds tick by, the line goes up, but it stays at the same horizontal position. Next, she drew a line that tilted to the right, labeled Path 2. Path 2 is a body moving at a constant speed. For every second of time that passes, it covers a certain amount of distance in space. It moves diagonally. Then a curved line, curving upward and outward. Path 3. Path 3 shows acceleration. The object starts slow, but as time goes on, it covers more and more distance. The line curves. Finally, she drew a squiggly, wavy line going up the center. Path 4. And Path 4 depicts a body going back and forth, zigzagging. Now, physics tells us something about these curved paths. Since Isaac Newton, we have known that a body will only accelerate or curve its path if a force acts on it. Path 4, for example, implies a push-pull force is shaking the object back and forth. And gravity? Aris asked. Where does gravity fit on your graph? That is the million-dollar question, Elara smiled. Gravity is one of several physical forces. But Einstein had a great insight. He noticed that gravity differs from all other forces in one crucial respect. End of note return. She summoned an image of the Leaning Tower of Pisa. Two objects, one large and heavy, one small and light, appeared at the top. The famous story of Galileo, Elara narrated. He dropped heavy and light bodies from the tower, to convince skeptics that they would hit the ground at the same time. And they did. Gravity affects all bodies equally. It doesn't matter if the object is hot, cold, living, dead, made of lead, or made of feathers. If you remove air resistance, they fall at the exact same rate. Eris said. Elara returned to the space-time graph. Elara returned to the space-time graph. If gravity were like an electric field, it would be picky. An electric field pushes charged particles, but ignores uncharged ones. Their paths on the graph would look different. But with gravity, everything follows the same path. Einstein reasoned that if the effect is the same for everyone, maybe it isn't a force at all. She reached out and grabbed the flat sheet of the graph in the hologram. With a twisting motion of her hands, she warped the grid. The straight lines bent. The flat paper became a rolling landscape of hills and valleys. Einstein proposed that it is better to represent the gravitational field not as a force acting in flat space-time, but as a geometrical property of space-time itself, she said. Imagine this sheet is the universe. I have curved it. Now look at the lines. She pointed to a line that looked wiggly on the curved surface. A wiggle in a path can be achieved in two ways, she said. You can draw a wiggly line on a flat sheet, which implies a force is pushing the pen back and forth. Or you can try to draw a straight line on a curvy sheet. The line tries to be straight. It follows the shortest path, the path of least resistance. But because the sheet is warped, the line appears curved. Quote, geodesics, Aris murmured. Yes, the straightest possible path on a curved surface. Einstein proposed that gravity is just objects following the natural curve of the universe. The Earth doesn't orbit the Sun because the Sun is pulling it with a tether. The Earth is trying to go in a straight line, but the massive weight of the Sun has dimpled the space around it, creating a valley. The Earth is simply rolling along the curve of that valley. So, we have replaced force with geometry, Aris summarized. And this leads us back to our problem. We need a wormhole. We need a specific type of geometry. But the Schwarzschild geometry, the black hole, is too aggressive. It destroys the bridge. Elara nodded. We need a geometry that is stable. To serve as a time machine, a wormhole has to be traversable. The traveler has to be able to pass through it and emerge intact. We established that the Schwarzschild wormhole pinches off too fast, but that model assumed the black hole was simple. It assumed it was not spinning. Aris said, his eyes lighting up. Rotation again, we return to the beginning. In the 1960s, physicists began studying spinning black holes, Elara said. She adjusted the simulation. The static black hole began to rotate. As it spun, it bulged at the equator like a flattened orange. Centrifugal force. It acts to oppose gravity. We know this from spinning on a merry-go-round. You get thrown outward. She pointed to the throat of the wormhole within the spinning black hole. In a static hole, gravity crushes the throat instantly. But in a spinning hole, the centrifugal force fights back. It pushes out against the gravity. This creates a balance. It raises the prospect that the wormhole throat might stay open long enough for something or someone to get through. "It sounds promising," Aris said. 40 years ago, many thought this was the answer. They imagined astronauts tumbling into spinning black holes and popping out in other universes. But on closer inspection, Elara said, her face darkening, the dream falls apart. There are problems. The first is purely practical. The gravitational forces are still horrific. She brought up the image of an astronaut approaching the spinning hole. "Imagine jumping out of an airplane, feet first," she said. "Gravity diminishes with height. Your feet are closer to the ground than your head, so they are pulled slightly harder. On Earth, the difference is microscopic. You don't feel it. But near a black hole, the difference is lethal." The holographic astronaut began to stretch, the body elongated, turning into a thin noodle. "Spaghettification," Elara said grimly. "Your feet are pulled so much harder than your head that you are ripped apart lengthwise. At the same time, because you are falling toward the center, your shoulders are squeezed together. You are stretched and crushed simultaneously." "A painful way to die," Aris noted. "If the black hole is small, say, the mass of our sun, you would be dead long before you reached the wormhole. You would be spaghetti," Elara confirmed. "To survive, you would need a supermassive black hole, one with 1 billion solar masses. The larger the hole, the gentler the tidal forces at the edge. You could survive crossing the horizon of a galaxy-sized monster. But that isn't a practical time machine. You can't build a galaxy in your backyard. And even if you could survive the stretching?" Aris asked. "Then you face the second problem," Elara said. "The blue sheet." "The radiation wall," Aris corrected. "Yes." The idealized model of a wormhole ignores the rest of the universe. It assumes the astronaut is the only thing falling in. But in reality, starlight, cosmic rays, dust, and gas are all falling in too. As they fall, gravity boosts their energy. By the time they reach the throat of the wormhole, this rain of light has become a tsunami of energy. It forms an impenetrable wall of radiation, a blue sheet of death right across the doorway. Its gravity would likely collapse the wormhole instantly, sealing it with the singularity. So, the spinning black hole is also a trap, Aris concluded. It offers a tantalizing glimpse of a tunnel, but guards it with lethal tidal forces and a wall of fire. And, Elara added, there is the issue of what lies at the center, the singularity. Singularity. And the centrifugal force of a spinning black hole fights gravity, Elara continued, zooming into the heart of the rotating dark sphere on the display. But it doesn't fight it enough to stop a singularity from forming. In a simple, non-spinning star, the collapse ends at a single point. But here, because of the spin, the star cannot shrink to a dot. Instead, it collapses into a ring. A glowing red circle appeared deep inside the black hole's wireframe model. A ring singularity, Aris observed, like the hole in a donut. Exactly. And this is where the theoretical gateway lies. If we ignore the radiation walls and the stretching forces for a moment, an astronaut could arguably fall into the hole, navigate carefully, and pass through the center of the ring without hitting the singularity itself. By missing the ring, she avoids being crushed to infinite density. She could then emerge into the other universe I mentioned earlier. Elara walked through the hologram, her hand brushing through the digital representation of the event horizon. But the idea that an astronaut might inspect a singularity and live to tell the tale strikes horror into the heart of a physicist. Taken at face value, a singularity is an entity with infinite density and infinite space curvature. It is an edge to space-time. There is literally nothing beyond it. It is a place where physical objects and physical laws cease to exist. It is the edge of the map, Aris said, where the dragons live. Worse than dragons, Elara corrected. If a singularity is an edge where things leave the universe, it can also be an edge where things enter. If you have a region of space where anything at all might emerge without cause and without warning, you have chaos. It would represent a total breakdown of the rational order of the cosmos. She turned to face the professor. This is why Sir Roger Penrose proposed a law of nature to ban such things. He called it the cosmic censorship hypothesis. He conjectured that nature finds naked singularities obscene. Therefore, they must always be decently clothed by event horizons black holes that trap light so we can't see the naked singularity inside. In that way, the chaos is hidden from the outside universe. No uncaused physical influences can leak out to wreak havoc on history. John, let there be no naked singularities. Aris quoted, precisely, but a traversable spinning black hole violates this. If you can fall in, zoom past the ring singularity, and come out again in another universe, then the gremlins from the singularity could come out with you. The singularity would be naked to that other universe. It breaks the rules. Why so? Aris sighed, clasping his hands behind his back. We are stuck. The static black hole kills you instantly. The spinning black hole might let you through, but it is lightly unstable, filled with lethal radiation, and violates the laws of cosmic order. Using a black hole as a gateway looks decidedly suspect. If our aim is to find a safely traversable wormhole, we need something else. We need something to combat gravity with more oomph. Elara nodded and waved her hand. The spinning black hole, the ring singularity, and the radiation walls all vanished. The room was empty again, save for the hum of the computer. The concept of time travel began with fiction, Elara said, changing the subject slightly. And curiously, the trigger that transformed it from fantasy into serious science was another work of fiction. A book cover appeared in the air, Contact by Carl Sagan. In the mid-1980s, the astrophysicist Carl Sagan was writing this novel, Elara explained. It was later made into a famous movie. The story isn't actually about time travel, at least not directly. It concerns a radio message received from an advanced alien civilization. The message contains the blueprints for a machine. A machine to build a wormhole, Aris anticipated. Yes. A wormhole connecting Earth to the star Vega, 26 light-years away. Sagan used the wormhole as a plot device to get around the speed of light. He wanted his characters to meet the aliens without spending thousands of years on a spaceship. In his story, they reach Vega in only a few minutes. Elara summoned a map of the stars. A glowing line connected the sun to a bright blue star, Vega. Sagan's wormhole was different from the ones we just discussed, she said. The black hole wormholes were gateways to other universes. Sagan's wormhole was a tunnel linking 2 points in the same universe, a subway tunnel through the galaxy. A shortcut, Harris noted. Sagan gave very few details in the book about how such a machine would work, Elara said. In the movie, Jodie Foster drops into a giant machine that looks like a spinning kitchen mixer. She zooms through a tunnel and pops out at Vega. It looked great on screen, but Sagan was a scientist. He wanted to know if it had any credibility. Was it just magic, or was it plausible physics? So he asked for help, Harris said. He approached his friend Kip Thorne at the California Institute of Technology. Thorne is a titan of gravitational physics. He and his colleagues agreed to check it out. They treated it as a serious problem, that they had to change their tactics. Elara brought up a diagram of a blank sheet of space. Usually, she explained, a physicist starts with an object, a star, a planet, a black hole, and uses general relativity to calculate the gravity it makes. We ask, here is a ball of matter. How does it curve space? Thorne did the opposite, Harris said. Reverse engineering, Elara nodded. Thorne started by writing down the answer first. He defined the geometry he wanted. He said, I want a wormhole with 2 mouths. I want it to be stable. I want it to be benign, meaning no crushing gravity, no infinite time warps, no radiation walls. It had to be a safe tunnel that a human could walk through. She drew a clean, perfect tube connecting 2 points on the holographic sheet. It looked smooth and safe, unlike the violent funnel of the black hole. Once he had the shape, Elara continued, he used Einstein's equations to work backward. He asked, if space is curved like this, what kind of matter is needed to create it? And the answer? Harris asked, leaning forward. The answer was trouble, Elara said. It became clear immediately that any familiar form of matter was out of the question. Water, rock, gas, plasma, even neutrinos, none of them work. All normal matter has positive mass. Positive mass creates attractive gravity. And attractive gravity tries to pull the walls of the wormhole together. If you made a wormhole out of normal matter, the throat would collapse before you could blink. So you need something to push back, Harris deduced. You need anti-gravity, Elara said. You need something to shore up the wormhole, to hold the walls apart against the crushing weight of space. You need a material that repels. She brought up a symbol on the screen, a negative sign. Anti-gravity has been a dream for a long time, she said. It is in folklore, myths of levitation, and UFO stories. It is the dream of wobbly inventors who want to float to the stars without rockets. But in serious science, it was usually laughed at. Einstein didn't laugh. Harris corrected. No. In 1917, Einstein actually put anti-gravity into his equations. Elara said. He added a term called the cosmological constant. At the time, he thought the universe was static, but gravity pulls everything together. So a static universe should collapse. To fix it, he invented a repulsive force to balance the attraction. He created anti-gravity to hold the universe up. End of quote. Then Hubble showed him the universe was expanding, Harris said, and Einstein called it his biggest blunder and threw the anti-gravity term away, Elara finished. Ironically, we now know he was right all along. Dark energy is a form of anti-gravity pushing the universe apart. But that is cosmic anti-gravity. It is too weak, too thin. To hold a wormhole open, we need something concentrated. We need exotic matter. Exotic matter, Aris repeated. It sounds like something from a comic book. It is a technical term, Elara replied, smiling. In physics, mass and energy are the same thing. $E equals mc squared, dollars. Normal matter has positive energy. Positive energy produces attractive gravity. To get repulsive gravity, anti-gravity, you need negative energy. Negative energy, Aris said. Positive energy gravitates. Negative energy anti-gravitates. It sounds impossible, Elara admitted. Well, like having a negative lunch. Either you have a sandwich or you have 0 sandwiches. How can you have less than 0 sandwiches? It depends on how you define 0, Harris suggested. Exactly. In relativity, 0 energy corresponds to empty space, flat space-time with no gravity. So, if we can engineer a situation where the energy is lower than that of empty space, we have negative energy. And that negative energy will create a repulsive gravitational field. Elara created a simulation of a box. Imagine a box filled with this exotic matter. If the total energy is negative, what happens? Does it float up? No, it falls down just like normal matter. But the gravity it creates is repulsive. If you placed a ball of normal matter next to this box, the ball would be pushed away. It blows things apart. So, Harris summarized, Thorne discovered that to make Sagan's wormhole work, you have to stuff the throat with exotic matter. You have to line the tunnel with negative energy. This anti-gravity pushes the walls out, fighting the natural tendency of space to collapse. It keeps the door open. And that, Elara said, was the breakthrough. Thorne and his students proved that traversable wormholes are theoretically possible. They don't violate the laws of physics, provided you can find or make this negative energy. It transformed the field. Suddenly, we weren't just looking for accidents in space, we were talking about engineering. And if you can build a wormhole that connects 2 points in space, Aris said, his voice dropping to a whisper, you have built more than just a subway. You have built a time machine. Yes, Elara said. Once the researchers digested the possibility of a wormhole in space, it dawned on them that the geometry could be twisted. If you move one mouth of the wormhole, or subject it to a different gravitational field, you desynchronize the time between the two ends. You turn a bridge across space into a bridge across time. So we have a blueprint, Aris said, breaking the silence that had settled over the Kronos laboratory. The hologram of the stable wormhole, a silver tube held open by the invisible scaffolding of negative energy, floated between them. But blueprints are cheap. Construction is expensive, especially when the building material is something that nature tries very hard to hide. Elara looked at the glowing negative signs, pulsing inside the wormhole's throat on the display. We need exotic matter. But you said earlier that we don't need to invent it from magic. You said known physical systems possess it. In tiny amounts, Aris corrected, walking around the perimeter of the simulation. We are not talking about mining it from a mountain. We are talking about the subtle behavior of the vacuum itself. Quantum physics tells us that empty space isn't truly empty. It is seething with activity, particles popping in and out of existence, energy fluctuating. Elora nodded, her mind racing back to her textbooks, the baseline energy of the universe. The baseline energy of the universe. The 0 point. Precisely, Aris said. And if we can create a condition where the energy drops below that baseline, we have negative energy. We have our anti-gravity. But to gather enough of it to hold open a wormhole big enough for a human, that is an engineering nightmare. We would need to harvest the whisper of the universe and turn it into a shout. He adjusted a dial on the console, and the wormhole simulation grew larger, dominating the room. The grid lines of space bent smoothly around it, flowing into the mouth at one end and emerging from the other. Let us assume, for the sake of the story, that a super civilization could do it, Aris proposed. Let's assume they can mine this negative energy and pack it into the throat of the wormhole. Now, we have a tunnel. A subway through the galaxy. But how does a subway become a time machine? That is the question that keeps physicists awake at night. Elara stared at the tunnel. It goes back to the speed of light. And Miss Bright. She summoned the text of the limerick again, letting it hover next to the high-tech wormhole. She started one day in the relative way and returned on the previous night. The wormhole is a shortcut, Elara explained, tracing a line through the air. Imagine I want to travel from Earth to the star Vega. It is 26 light-years away. If I fly a spaceship through normal space at 90% of the speed of light, it will take me just over 26 years to get there. Light takes 26 years. I arrive just after the light does. Correct, Aris said. But now, suppose we have a wormhole connecting Earth and Vega, Elara continued. The throat is short, maybe only a few kilometers long. I step into the mouth on Earth, walk a few kilometers, and step out on Vega. The journey takes me, what? An hour? Let's say an hour, Aris agreed. So, I have traveled from Earth to Vega in 1 hour, Elara said, her eyes widening as the implication landed. But light, traveling the long way around through normal space, takes 26 years. I have beaten the light beam. I have outpaced the universal speed limit, not by going faster locally, but by taking a path that is shorter. And that, Aris pointed out, is the trigger. If you can outpace light, you can mess with time. Elara manipulated the simulation. She placed a clock on Earth and a clock on Vega. Here is the trap, she said. In the wormhole, the two mouths are connected. If I look through the wormhole from Earth, I see Vega as it is now. If I step through, I am on Vega now. But if I look at Vega through a telescope across normal space, I see Vega as it was 26 years ago, because the light took that long to reach me. Now complete the circuit, Aris urged. Be Miss Bright. Okay, Ilara said, focusing on the logic. I step through the wormhole. I arrive at Vega. The trip took essentially 0 time. I am on Vega. Now, suppose I turn around and fly back to Earth through normal space. But I have a super ship. I fly back at nearly the speed of light. Go on. If I fly back through normal space, Ilara said slowly, I am chasing the light that left Earth 26 years ago. No, wait. That's not it. She frowned, the paradox tangling in her mind. It's about the loop. A closed loop in space becomes a loop in time. Think about now, Aris guided her. The wormhole connects Earth now with Vega now. But outside the wormhole, space and time are linked. If you travel fast, time slows down. To turn this subway into a time machine, we have to do more than just connect 2 places. We have to desynchronize them.
Ilara's hands flew over the controls.
We have to move the mouths. She grabbed the holographic representation of the wormhole mouth located on Earth. The other mouth remained fixed near Vega. If I take the Earth mouth, Ilara hypothesized, and I put it on a spaceship, I fly it away at high speed, near the speed of light, and then bring it back. What happens to the clock inside that mouth? Special relativity applies, Aris said softly. Moving clocks run slow. Right. So, the wormhole mouth on the spaceship ages less than the mouth that stayed still. Let's say the trip takes 10 years of Earth time. But because of the speed, the clock on the moving mouth only ticks forward by 1 year. So you bring the mouth back to Earth, Aris said. Park it on the lawn. What do you have? I have 2 mouths sitting next to each other, Ilara said, visualizing the scene. One is the stationary mouth. It has aged 10 years. The other is the traveled mouth. It has aged only 1 year. But, and this is the crucial part, they are still connected on the inside. And the tunnel inside creates the link, Aris added. The tunnel connects them instantly, Ilara said, her voice rising with excitement. So, if I look into the young mouth, I am looking 5 years into the past? No, 9 years, the difference in their ages. Exactly, Aris said. The wormhole connects 2 different times. One mouth is in the present. The other mouth, because of the time dilation it suffered during the journey, is anchored in the past. You have created a bridge not just across space, but across the years. Ilara stared at the 2 silver rings in the hologram. They sat side by side, innocuous, yet they represented a tear in the fabric of causality. So, if I step into the young mouth, she whispered, I emerge from the old mouth, but 9 years ago? Or do I step into the old mouth and come out the young one? Think of it like a window, Aris said. The wormhole connects specific moments. If the time difference is 9 years, stepping through one way sends you 9 years back. Stepping through the other way sends you 9 years forward. You could step through, go back to the past, and then walk over to your younger self and say hello. You could give yourself the winning lottery numbers. Causal chaos, Ilara muttered, recalling the phrase from her research. This is what the text meant. it would be possible to reverse cause and effect. If I can visit the past, I can change the past. And if I change the past, I might prevent myself from entering the wormhole in the first place. The grandfather paradox. Aris nodded. The classic nightmare. If you go back and kill your grandfather, you are never born. If you are never born, you never go back. If you never go back, your grandfather lives, and you are born. It is a logical impossibility. And yet, general relativity seems to allow the machine to be built. So, does the universe just explode? Elara asked, half seriously. If I build this time machine, does reality shatter? Some physicists think so, Aris said. Stephen Hawking suggested the chronology protection conjecture. He believed that the universe hates time machines even more than it hates naked singularities. He thought that as soon as you try to turn your wormhole into a time machine, as soon as you try to close that time loop, something will happen to destroy it. Like the radiation war? Elara asked. Exactly like that. Vacuum fluctuations. That negative energy we use to hold the throat open. It might backfire. As the time machine activates, energy might loop through the wormhole, circle back in time, go through again and again, infinitely amplifying in a split second. A feedback loop of pure energy. It would vaporize the wormhole the instant it became a time machine. Oh, nature protecting herself, Elara mused. Destroying the bridge to save the timeline. But, Aris said, raising a finger, we don't know for sure. The math is fuzzy. It depends on how you combine quantum mechanics with gravity. And we don't have that theory yet. Until we do, the wormhole time machine remains a tantalizing possibility. A doorway that physics permits, but engineering might never achieve. Elara looked at the simulation one last time. The two mouths, the bridge across time, the swirling, exotic matter. It all comes down to the geometry, she said. The shape of space. Van Stockham used a cylinder. Gödel used the whole universe. Thorne used a wormhole. They're all just different ways of folding the paper. Yes, Aris agreed. Sculptures in the structure of space. We have learned how to create the tunnel. We have learned the dangers of the black hole. We have hypothesized the exotic fuel. But there is one question we haven't fully answered. We talked about how to make it. But we haven't talked about what it would actually feel like to use it. To be the traveler. He turned to her, his expression serious. Let us run one final simulation, Elara. Not of the physics equations, but of the journey. Let us simulate the experience of the observer. If you were to stand at the threshold of that wormhole, looking into the throat, what would you see? What does the past look like through the lens of a space-time tunnel? Elara nodded and cleared the board. Visualizing the transit, she commanded the computer. Destination, yesterday. The simulation hummed to life, filling the Kronos laboratory with the illusion of deep space. The metal walls dissolved into the velvet black of the cosmos, studded with the diamond-hard light of distant stars. Elara and Professor Aris stood on a virtual platform, seemingly floating in the void. Directly ahead of them, the wormhole awaited. "It does not look like a funnel," Elara observed, her voice hushed by the grandeur of the projection. "In all the textbook diagrams, it looks like a whirlpool or a funnel dipping down into a rubber sheet. But here, that is because the rubber sheet is a two-dimensional analogy," Aris explained, his avatar standing beside her. "We live in 3 dimensions. When you take a two-dimensional circle and expand it into 3 dimensions, it becomes a sphere. A wormhole mouth in our universe would look like a crystal ball hanging in space. And so it did. The entrance to the time machine was a perfect, shimmering sphere. It was not black like the hole they had studied earlier. Instead, it was a window. The surface of the sphere showed a distorted image of the stars on the other side, or, in this case, the other time. "We are looking at the destination," Elara said, stepping closer to the floating orb. "But because this is a time machine, we are also looking at the past. If we configured the time shift for 12 hours, the image inside that sphere is Earth as it looked 12 hours ago." Quote, "Walk around it," Aris suggested. Elara moved around the sphere. As she did, the image inside shifted, just like looking through a glass lens. She could see the curvature of the Earth inside the ball, but the cloud patterns were different from the real Earth behind her. "It is like a spherical mirror," she said, "but instead of reflecting the world, it reveals a different one." "Now step inside," Aris commanded. "Let us see the throat." Elara took a deep breath and stepped off the platform, drifting into the sphere. The transition was seamless. There was no sensation of hitting a surface. One moment she was outside, the next the universe warped. She was now inside the tunnel. The view was dizzying. All around her, in every direction, she saw the distorted light of the universe. It was as if she were inside a kaleidoscope. "This is the throat." Aris's voice came from everywhere at once. "You are standing on a bridge of exotic matter. Look at the walls." Elara looked. The walls of the tunnel were not made of rock or metal. They were made of the negative energy field they had discussed, the anti-gravity scaffolding holding the space-time open. It shimmered with a violet hue in the simulation, a visual representation of the repulsive force pushing outward, fighting the crushing weight of the universe that wanted to snap the tunnel shut. If this energy failed for even a microsecond, Aris noted, the tunnel would pinch off. You would be crushed into a singularity. But as long as the negative energy holds, the path is safe. Walk forward. Elara moved through the tunnel. It felt short. In the logic of the wormhole, the distance between the two mouths might be only a few meters, even if the distance in the outside world was light years. Or, in this case, the distance in time was years. "I am reaching the other side," she said. A new sphere of light appeared ahead, the exit. She stepped through it and emerged back into the vacuum of space. She turned around. The spherical mouth was behind her now, showing the future she had just left. But in front of her was Earth. "Welcome to yesterday," Aris said, appearing beside her again. "You have traveled back in time. You are now a part of history." Elara looked at the blue planet. It feels normal. I don't feel different. The universe doesn't feel broken. Not yet, Aris said darkly. But now comes the test. The paradox. Quote, he waved his hand, and a new object appeared in the simulation. It was a simple radio transmitter floating in space near them. This is the grandfather paradox in its simplest form, Aris explained. Or rather, the auto-infanticide scenario. Let us assume that this transmitter is programmed to send a signal through the wormhole. The signal will go into the future mouth, travel back in time, and emerge from the past mouth, the one we are standing next to right now. Okay, Elara said, following the logic. The signal carries a command, Aris continued. The command is, shut down the transmitter. So the transmitter sends a signal into the past. The signal arrives in the past, which is now, and tells the transmitter to turn off before it ever sends the signal. Elara frowned. If the transmitter turns off in the past, it never sends the signal in the future. If the signal is never sent, the transmitter is never told to turn off, so it stays on. So it sends the signal, so it turns off. It's a loop, a contradiction. Logic collapses. Precisely, Aris said. A closed causal loop that creates an impossible situation. Logic demands that the event is either A or not A. It cannot be both. So, what happens? Does the universe crash like a computer with a bad line of code? Elara watched the transmitter in the simulation. Let's run it. See what the computer predicts. Initiating paradox protocol, the computer's mechanical voice announced. The transmitter hummed. A beam of red light shot out, aiming for the wormhole mouth. It was about to enter the tunnel, to travel back in time, to kill itself. But just as the beam fired, a small piece of space debris, a rock no bigger than a fist, drifted into the path. The laser beam hit the rock, deflected slightly, and missed the wormhole mouth. The signal never went back in time. The transmitter remained on. It missed? Elara said, surprised. Is that a glitch? No, Aris said. That is the Novikov self-consistency principle. The what? Igor Novikov? Aris said. A Russian physicist. He argued that if time travel is possible, the laws of physics must enforce consistency. You cannot change the past. There is only one timeline. If you go back in time and try to kill your grandfather, something will always go wrong. The gun will jam. You will slip on a banana peel. A rock will block the laser. The universe will conspire to prevent the paradox, because the paradox is impossible. You can visit the past, but you cannot alter it. You were always part of the past. Elara looked at the floating rock. So, free will is an illusion? If I went back and tried really, really hard to change something, the universe would just force my hand. According to Novikov, yes, Aris replied. You are an actor on a stage where the script has already been written. You can move around, say your lines, but you cannot change the ending. The loop is closed. The snake eats its own tail, but it never chokes. That sounds suffocating, Elara admitted. Is there another option? There is, Aris said. The many worlds interpretation, he snapped his fingers. The simulation reset. The transmitter appeared again. The rock was gone. In quantum mechanics, Aris explained, some physicists believe that every time a decision is made, the universe splits. If you flip a coin, the universe divides into two branches, one where it lands heads and one where it lands tails.
Parallel universes, Elara said.
Yes. If this is true, then time travel becomes a messy business of hopping between branches. If you go back in time and kill your grandfather, you haven't killed your grandfather. You have killed the grandfather in a parallel timeline. In that new timeline, you are never born. But in your original timeline, the one you left, your grandfather is still alive, and you still exist. You haven't changed your past. You have just created a new, tragic future for a different universe. So no paradox, Elara said. Just a lot of different worlds. Exactly. David Deutsch, a pioneer of quantum computing, championed this idea. He argued that quantum mechanics saves us from the paradox. The wormhole doesn't link today to yesterday in the same timeline. It links today in universe A to yesterday in universe B. Elara looked at the wormhole sphere again. So, if I stepped through there, I might never be able to get back to my original home. I would be stranded in a copy. A distinct possibility, Aris agreed, and a terrifying one. Imagine returning home to find that everything is the same, but slightly different. Your keys don't fit the lock. Your friends don't remember the conversation you had yesterday. You are a ghost in a world that is not yours. The simulation began to fade. The stars dimmed, and the metal walls of the Kronos laboratory reasserted themselves. The immersive magic of the wormhole transit vanished, leaving them back in the cold, hard reality of the lab. These are the theories, Aris said, leaning against the main console, looking tired. Van Stockham's cylinders, Gödel's rotating universe, rotating black holes, wormholes held open by exotic matter. Self-consistency principles versus branching universes. We have built a magnificent cathedral of mathematics. But, Elara said, sensing the shift in his tone, it is still just math. Can we actually build it? Or is this all just a game for physicists? Aris took off his glasses and polished them slowly. That is the final hurdle, Elara. We know how to draw the blueprints. We know what fuel we need, but do we have the tools to manipulate the fabric of reality on such a scale? The answer lies not in the stars, but in the very small, the microscopic. If we are to build a time machine, we cannot start with galaxies. We must start with atoms. He gestured to the screen, where a new heading appeared, signaling the next phase of their inquiry. We have discussed how to visit the past, Aris said, but we have ignored the most fundamental question of all. Not how do we build it, but where is the time? Elara looked at him, puzzled. I don't understand. We assume time is a river that flows, Aris said. But what if it isn't? What if the past is not a place we go to, but a place that is already here, frozen, waiting for us to unlock it? To understand time travel, we must understand the nature of time itself. And for that, we must leave the wormholes behind and look at the block universe. The block universe, Elara repeated, the term feeling heavy on her tongue. It sounds static, like a block of concrete. A block of ice might be a better metaphor, Professor Aris said, walking to the center of the room. He tapped the console, and the star maps vanished. In their place, a large, translucent block appeared. It was rectangular, glowing softly with a blue inner light. Imagine this block represents all of space-time. Every point inside it is an event. A birthday, a sunrise, a war, a first kiss. Okay, Elara said, circling the holographic block. In our everyday lives, we feel like we are moving through time, Aris explained. We think the past is gone, vanished into memory. We think the future hasn't happened yet. We think the only thing that is real is the now, this razor-thin slice of the present moment. He waved his hand, and a thin, glowing red sheet appeared, slicing through the block vertically. It moved slowly from one end to the other like a scanner. This red sheet is what we call now, Aris said. As it moves, it turns the future into the past. This is how we experience life, flowing, changing. But physics disagrees, Elara guessed. Einstein disagreed, Aris corrected. When Einstein unified space and time into a single entity space-time, he suggested that the distinction between past, present, and future is only a stubbornly persistent illusion. If you look at the equations of general relativity, nothing is moving. The block just is. Aris froze the moving red sheet in the middle of the block. Look at the block as a whole, he said. The beginning of the block is the Big Bang. The end is the heat death of the universe. They exist simultaneously in the geometry of space-time. The dinosaurs are still roaming the Earth at their coordinate in the block. Your great-grandchildren are already born at their coordinate. The past hasn't been destroyed, and the future isn't waiting to be built. It is all there, frozen in the four-dimensional crystal. Elara stared at the block. So, if I use a time machine to go back to 1923, I'm not rewinding a tape. I'm just moving my position to a different part of the block. Exactly, Aris said. You are traveling to a location, just like traveling from London to New York. New York exists even when you aren't there. The year 1923 exists right now, just down the road, in the time dimension.
That makes time travel seem
less magical, Elara noted, and more like geography. It is geography, Aris smiled. Chronogeography. And the wormhole, perfectly still familiar. It is a tunnel bored through the block. He manipulated the hologram. A small silver tube appeared, cutting a curved path through the block, connecting the red sheet of the present to a section of the block labeled past. Without the wormhole, Aris said, you are stuck on the red sheet, forced to move forward at 1 second per second. But the wormhole lets you step out of the normal flow, take a shortcut through the bulk of the block, and re-enter at an earlier coordinate.
Elara looked closer at the tunnel.
But if the future is already in the block, does that mean my decision to build the time machine is already written there? Do I have a choice? That, Aris sighed, is the philosophical hangover of the block universe. If the future already exists, then free will is the casualty. We are just sliding along a track that was laid down at the beginning of time. If you build the machine, it is because you were always going to build it. If you fail, you are always going to fail. I don't like that, Elara admitted. I like to think I'm in control. Most humans do, Aris agreed. But let us return to the physics. We have our block universe. We have our wormhole tunnel connecting 2 points within it. We have our exotic matter keeping the tunnel open. We have established that the math works. But we have avoided the most practical problem of all, which is energy. Aris stated flatly. We have talked about negative energy as if it were something you could buy at a hardware store. But do you realize the scale we are talking about? Elara shook her head. The textbook said, tiny amounts are found in the vacuum. Tiny amounts are found in the vacuum, Aris confirmed. But to hold a wormhole open, a wormhole big enough for a human to walk through, say, 1 meter wide, you need a lot of it. And when I say a lot, I don't mean a truckload. I don't mean a power plant. He cleared the block universe simulation and brought up an image of the Earth. Then, the image zoomed out to show the sun. Then, it zoomed out further to show the galaxy. To keep a 1 meter wormhole throat open, Aris said, his voice serious, you need an amount of negative energy equivalent to the total mass of the planet Jupiter. And you need it concentrated into a band of space thinner than a single atom. Elara's jaw dropped. Jupiter? But that's impossible. It is discouraging, Aris admitted. And that is just to hold the door open, to create the wormhole in the first place, to rip the fabric of space and glue 2 distant points together. That requires energy on the scale of a supernova. We are talking about the energy output of billions of stars, focused into a single point. Quote, so, Sagan's machine in contact, pure fiction in terms of energy, Aris said. He assumed a super civilization could do it. Maybe a civilization that can harness the power of entire galaxies. But for us, for humans in the 21st century, it is like an ant trying to build a skyscraper. Elara slumped slightly against the railing. So it's over. The math says yes, but the energy says no. Not necessarily, Aris said, a glint in his eye. There is always a loophole. Physics is the art of finding loopholes. We assumed we have to build a wormhole from scratch. That is expensive. But what if we found one? The Big Bang, Aris said, summoning an image of the violent white-hot explosion that birthed the universe. It was a messy event. Chaos. Immense energies. Some physicists, like Stephen Hawking, suggested that in that first fraction of a second, tiny wormholes were created naturally, primordial wormholes. Microscopic ones, Elara guessed. Yes, subatomic, smaller than an electron. They might still be out there, floating in the foam of space-time, left over from the beginning. But I can't fit through a subatomic wormhole, Elara pointed out. No. But space is elastic, remember? Aris said. If you could capture one of these tiny, natural wormholes, and if you could pump energy into it, you might be able to inflate it, expand it, grow it from the size of a proton to the size of a doorway. Is that easier than building one from scratch? It is the difference between building a mountain and finding a small rock and making it bigger, Aris said. Still incredibly difficult. Still requiring vast amounts of negative energy to stabilize it once it is grown. But it moves the problem from impossible to merely astronomical. Elara looked at the simulation of the Big Bang, the debris flying outward. So, the recipe for a time machine is find a leftover wormhole from the dawn of time. Capture it. Inflate it using the energy of a solar system. Stabilize it with negative energy harvested from the vacuum. And then accelerate one mouth to the speed of light to desynchronize the clocks. A simple grocery list. Aris chuckled. But there is one more thing, Elara said, her mind working through the list. We talked about the machine destroying itself, the chronology protection conjecture, the feedback loop. Ah, yes, Aris said. Aris said, the final guardian, even if you find the energy. Even if you inflate the wormhole, even if you stabilize it, the moment, the very instant, you turn it into a time machine. Nature might step in. He brought up the image of the wormhole again. This time, he drew a single beam of light entering the right mouth. Imagine this is a photon of radiation, Aris described. It enters the mouth. It travels back in time. It emerges from the left mouth in the past. It travels across the room and enters the right mouth again. It goes back in time again. It emerges again. It does this over and over. The beam of light in the hologram began to circle rapidly, becoming a solid ring of brightness. Because light travels so fast, Aris said, it can make this loop billions of times in a second. Each time it loops, it adds its energy to the beam. It amplifies. It becomes a laser of infinite power. A resonance catastrophe, like a microphone screeching when it gets too close to the speaker, Elara said, wincing at the thought. Vacuum fluctuations, that quantum noise we talked about, would get caught in this loop. They would pile up. The energy density at the throat would skyrocket to infinity. The wormhole would either vaporize or collapse into a black hole before you could even take your first step. So Hawking was right? Elara asked. The universe protects history by destroying the bridge. Perhaps, Aris said. But there are counter-arguments. Some calculations suggest the beam might defocus, or that quantum gravity effectively cuts off the energy before it becomes infinite. We don't know. We are standing at the edge of our knowledge, peering into the fog. He turned off the main projector. The room went dark, save for the emergency lights along the floor. It is a sobering thought, Aris said quietly. We have spent the last hour discussing how to conquer time. But in the end, time seems to defend itself with walls of fire, impossible energy bills, and logical paradoxes. Quote, "So why do we do it?" Elara asked. "Why do we keep writing the papers? Why did Van Stockham and Gödel and Thorne bother?" "Because of the what if," Aris said. "And because, Elara, even if we never build the machine, the study of it teaches us about where we live. By asking, can we travel to the past, we learned that black holes are real. We learned about the Big Bang. We learned about the expansion of the universe. The dream of time travel drives the reality of physics. Wah. The dream was a time travel physics, until the state was finally gone. The place that soothed her name with a bigger sister. When they stayed once and again. We have looked at the physics, the math, and the philosophy, but we haven't looked at let's call it the tourism, the sociology. Suppose, just for a moment, that we succeed. Suppose we beat the odds. We build the machine. We stabilize the throat. We solve the feedback loop. We open the door to 1923. What then? Elara asked. Who goes? Aris asked back. And more importantly, why are they not here already? It is the Fermi paradox of time travel, Aris declared, pacing slowly across the dark floor of the laboratory. In astronomy, Enrico Fermi asked, if the universe is teeming with life, where is everybody? Why haven't we seen the aliens? With time travel, the question is, if humanity or any other civilization ever survives to build a time machine, why aren't they here now? Why aren't our history books full of tourists from the year 4000 taking selfies at the Battle of Hastings? Elara considered this. Maybe they are hiding, like a prime directive in Star Trek. They observe but don't interfere. Perhaps, Aris said. But humans are terrible at keeping secrets. And if time travel becomes cheap and accessible, like air travel is today, surely someone would break the rules. A teenager joyriding. A historian trying to save the Library of Alexandria. A criminal trying to kill a rival before they are born. We see no evidence of this. The past seems stubbornly undisturbed. He stopped and turned to the holographic projector. There is a famous experiment concerning this. Stephen Hawking, the great physicist, held a party. Party, yes. On June 28th, 2009. He filled a room with balloons and champagne. He sat there and waited. He waited for hours. But he didn't send the invitations until after the party was over. The invitation said, "You are cordially invited to a reception for time travelers." He figured that if time travel works, someone in the future would find the invitation and come back to the party. And? Elara asked, though she suspected the answer. Nobody came, Aris said. Hawking sat alone. The champagne went flat. He took this as experimental evidence that time travel into the past is impossible. Quote, Elara looked at the empty virtual room on the display. End quote. It makes sense. If they didn't show up, they don't exist. Unless, Aris said, raising a finger, There is a catch, a fundamental limitation of the machine itself, a rule that explains why the party was empty and why we don't see tourists. He manipulated the wormhole simulation again. He showed the two mouths, mouth A, Earth, and mouth B, space. Remember how the machine works, he said. We build a wormhole today. Let's say the year is 2050. We keep mouth A in the lab. We put mouth B on a spaceship and fly it near the speed of light for a while, then bring it back. Because of time dilation, mouth B is younger. Let's say 10 years younger. Okay, Elora followed. So mouth B is anchored in 2040 and mouth A is in 2050. Exactly. You can enter mouth A in 2050 and step out of mouth B in 2040. You have traveled back 10 years. But, and this is the critical part, can you travel back to 1923? Can you travel back to see the dinosaurs? Elora stared at the diagram. The logic clicked into place. No, because the wormhole didn't exist then. Precisely, Aris beamed. You can only go back as far as the moment the machine was created. The past mouth B, is the limit. It is the anchor. You cannot step off the end of the bridge into a time before the bridge was built. It's like the telephone, Elora realized. Alexander Graham Bell invented the telephone in 1876. He could call Watson in the next room, but he couldn't make a call to George Washington in 1776. Even if the phone existed in 1876, there was no receiver in 1776 to pick up the call. That is the perfect analogy, Aris agreed. The wormhole is a receiver. Until you build the first one, the line is dead. This explains Hawking's empty party. Hawking held his party in 2009. If the first time machine isn't built until the year 3000, the people of the future can travel back to 3000, but they cannot go back to 2009. The road stops at the construction site. Elora looked at the imaginary timeline floating in the air. So, history is safe. The dinosaurs are safe. Miss Bright can't go back to the previous night unless she'd built a machine the night before. Yes. History is safe from us, Aris said. But think about the moment we switch it on. Think about day one. He tapped the console. A date appeared. August 12th, 2100. Let's pretend this is the day we successfully activate the first stable wormhole time machine. We turn it on. We stabilize the throat. We accelerate the mouth to create a 1-hour time difference. It works. Okay. At that precise moment, Aris said, his voice dropping to a whisper, we have connected the present to the future, forever. That day, August 12th, 2800, dash becomes year zero. It becomes the deepest possible past that anyone in the future can visit. So, Elora hesitated, a shiver running down her spine. If the machine stays on for 1,000 years, then a historian from the year 3100 can travel back to 2100. Correct? And a tourist from the year 5000 can travel back to 2100. And a student from the year 10,000 can travel back to 2100. All of eternity can funnel back to that single point. The moment the door was opened, Aris gestured to the empty space in the lab. The moment we turn that machine on, Ilara, we shouldn't expect silence. We shouldn't expect an empty room like Hawking did. We should expect a stampede. We should expect cameras, flashes, flying ships, and billions of eyes peering out of the wormhole mouth. The moment of activation is the moment we make contact with the entirety of the future. Elara imagined it, the machine humming to life, and instantly the throat filling with the light of 1,000,000 future civilizations, all clamoring to see the first moments of the time age. It would be the end of privacy, she whispered. The Panopticon. If they can come back, they can watch. History stops being a matter of interpretation and starts being a matter of surveillance. No more secrets. Every crime, every whisper, every closed-door meeting. If it happens after the machine is built, the future can rewind the tape and watch it. It changes the nature of humanity, Aris said solemnly. We live our lives assuming that our mistakes fade. That time washes away the details. But with a time machine, nothing washes away. The past becomes a permanent museum exhibit. We become the exhibits. That sounds terrible, Elara said. Maybe it's better if we can't build it. Maybe, Aris conceded. Or maybe, just maybe, the future has laws. Maybe the time police are real. Maybe the wormhole is heavily guarded, and only authorized scientists are allowed to look through the glass. He swiped the timeline away, leaving them in the dim light of the lab again. But there is one final destination we need to discuss, Aris said, shifting the tone. We have talked about the past. We have talked about the paradoxes of yesterday. But the equations of general relativity don't just point backward. They also point forward. And if you follow the arrow of time to its absolute limit, you reach the ultimate question. The future? Elara asked. Not just the future of human history, Aris clarified. The future of the universe itself. The end. You see, Elara, time travel is usually a fantasy about fixing human mistakes. Killing Hitler, saving a loved one, winning the lottery. It is small thinking. It is parochial. He walked to the window, looking out at the night sky. But if you have a machine that can bridge the eons, if you have a ship that can bypass the long, slow crawl of entropy, then you have a way to escape the ultimate fate. You have a lifeboat. A lifeboat for what? For the heat death, Aris said. For the big freeze. The universe is dying, Elara. Slowly, yes. But surely. Stars will burn out. Galaxies will drift apart. Black holes will evaporate. Eventually, the cosmos will be cold, dark, and empty. That is the destiny written in the laws of thermodynamics. Elara felt a sudden heaviness. It was a concept she knew, but hearing it spoken aloud in the context of their journey made it feel immediate. But Aris turned back, his eyes gleaming with a strange intensity. If we can master the wormhole, do we have to die with it? Or does the machine offer a back door? An escape hatch from the end of time? Elara looked at the dormant computer. You mean leaving the universe? I mean cheating the Reaper on a cosmic scale, Aris said. Let us run the final simulation. Not of the past, but of the ultimate future. Let us see what happens when we push the time machine to the very edge of existence. Initiating the Omega Protocol, Aris announced, his voice echoing with a somber gravity. He typed a command sequence into the console that was far longer and more complex than the previous ones. The Kronos laboratory did not just darken this time. It seemed to dissolve completely. The holographic emitters pushed their limits, projecting a view of the galaxy not as it was, but as it would be. The familiar spiral arms of the Milky Way appeared, but they were different. They were dimmer. The vibrant blues and whites of young stars were gone, replaced by the dull, dying embers of deep reds and fading oranges. We are moving forward, Aris narrated, watching the galaxy spin sluggishly. Not 10 years, not 1,000 years. We are jumping billions of years per second. We are watching the long, slow exhalation of the cosmos. Elara watched as the lights began to wink out. One by one, the stars were dying. Stars are engines, Aris said. They burn fuel. Hydrogen fuses into helium. Helium fuses into carbon. Eventually, the fuel runs out. Small stars fade away quietly. Massive stars explode and leave behind black holes or neutron stars. But eventually, the star formation stops. The gas clouds are exhausted. On the screen, the galaxy was now a ghost town. It was populated only by black holes, neutron stars, and cooling white dwarfs. This is the era of degeneracy, Elara whispered, remembering the term from her cosmology classes. Yes, but we must go further, Aris urged. Keep watching. The simulation accelerated. The white dwarfs cooled into black dwarfs cold, dead lumps of crystal floating in the dark. The galaxies themselves began to break apart, their gravitational glue failing as they drifted into the infinite void of an ever-expanding universe. The big freeze, Aris said. Entropy, the second law of thermodynamics, states that in a closed system, disorder always increases. Heat flows from hot to cold until everything is the same temperature. When the universe reaches equilibrium, no energy can flow. No work can be done. Life becomes impossible. Thought becomes impossible. Time itself loses meaning because nothing changes. Close quote. The room was now pitch black. The only light came from the faint control board on Aris's wrist. This is the destiny of our universe, Aris said softly in the dark. Cold, dark, empty, forever. It is a tragedy on a scale we cannot comprehend. All music, all art, all science, all love it all ends here, in the silence of the freeze. Elara felt a cold knot in her stomach. So what is the point? If everything ends, why does it matter what we do? That is the question of the nihilist, Aris said. But the engineer asks a different question. The engineer asks, is there a way out? A single point of light appeared in the center of the room. It was tiny, no bigger than a marble, but it burned with a fierce, violet intensity. "The wormhole," Elara said. "The lifeboat," Aris corrected. "We have discussed using wormholes to travel to the past, yesterday, or the future, tomorrow. But the wormhole connects two regions of space-time. What if the second region isn't in this universe at all?" He expanded the simulation. The black void of the dead universe was shown as a flat, dark sheet, but hovering above it was another sheet, bright, glowing, and vibrant. "The multiverse theory," Aris explained. "String theory and inflation theory suggest that our universe might not be the only one. We might be just one bubble in a vast cosmic foam. While our universe is old and dying, another universe might be just being born. A baby universe, hot and fresh and full of energy." Elara looked at the glowing sheet above. "And the wormhole bridges the gap?" "Hypothetically, yes. If a civilization at the end of time could gather the last remaining scraps of energy, harvesting the rotational energy of the last supermassive black holes, they might be able to punch a hole through the fabric of their dying reality." Aris manipulated the light. The violet marble stretched into a tunnel. It punctured the dark sheet of the dead universe and extended upward, connecting to the bright sheet of the new universe. "An umbilical cord," Aris described. "A bridge from the old world to the new. A Type 3 civilization. One that can harness the power of an entire galaxy. Could build this. They could pack their knowledge, their genetic codes, perhaps even their consciousness, into a data arc. They could send this arc through the wormhole, escaping the big freeze and arriving in a young universe, ready to start again. Quote, "Like a seed drifting across the ocean to find a new island," Elara mused. "Exactly. It transforms the wormhole from a curiosity into a necessity. It isn't just a machine for sightseeing. It is the mechanism of survival for intelligent life. Without it, intelligence is a fleeting spark that burns out and is forgotten. With it, intelligence becomes immortal. It can migrate from universe to universe, staying one step ahead of the decay." The simulation showed tiny ships traveling through the violet tunnel, leaving the darkness behind and emerging into a blinding white light of a new Big Bang. "So," Elara said, her voice filled with wonder, "we aren't just studying time travel. We are studying the escape plan for existence itself." "That is the grand hope," Aris said. "But there is a catch. There is always a catch." He snapped his fingers, and the lights in the lab slowly returned to their normal, sterile hum. The grand vision of the multiverse faded, leaving them back with their chalkboards and monitors. "The catch is that we don't know if the wormhole connects to a safe place," Aris said, leaning back against a desk. "A baby universe is a violent place. Incredible heat. Infinite density. It is not a garden. It is a furnace. To send a traveler through, you would need a destination that is habitable. You would need to target the exit mouth with impossible precision." Quote, "And," Elara added, realizing another problem, "if we travel to a new universe, we can never come back. The wormhole would likely snap shut behind us. It is a one-way trip." "A one-way trip to the unknown," Aris agreed. "But compared to the certainty of death in a freezing universe, The unknown is a gamble worth taking. He walked over to the main blackboard, which was covered in equations describing the tension of the wormhole throat. He picked up a piece of chalk and circled a specific symbol. T. We have covered the history, Aris summarized. From Van Stockham's spinning cylinders to Gödel's rotating universe, from the event horizons of black holes to the exotic matter of Thorne's wormholes, we have looked at the paradoxes killing grandfathers and empty parties, and we have looked at the ultimate destiny escaping the end of time. He dusted the chalk from his hands. But Ilara, all of this, all of these simulations, these theories, these papers, bare. They rely on one fundamental assumption. They assume that the human mind is capable of understanding the true nature of time. We assume time is a line, or a circle, or a river. But what if it is none of those things? Ilara frowned. What else could it be? We perceive time because we have memory, Aris said, tapping his temple. We remember the past, but we don't remember the future. This asymmetry creates the feeling of flow. But in the quantum world, the world of the very small, there is no arrow of time. Processes can run backward just as easily as forward. An electron doesn't know what yesterday is. He turned to her, his expression intense. The final part of our journey isn't about the machine, it's about the user. It's about consciousness. Some physicists argue that time is a construct of the brain, that the block universe exists all at once, and our consciousness is just a spotlight moving through it. If that is true, then building a time machine might not require exotic matter or black holes. What would it require? Ilara asked. It would require changing the spotlight, Aris said enigmatically. It would require hacking the observer. But that is metaphysics. Let us stick to the physics for now. He gestured to the center of the room. We have one final simulation to run. We have talked about the theory. Now, I want to show you the reality. I want to show you the design. The design? Ilara asked. You mean we actually have a design? We have a prototype, Aris revealed, a mischievous smile playing on his lips. Not a working machine, of course. We don't have the mass of Jupiter, but we have a mathematical prototype, a design for a test. A way to send a single particle, a single photon, back in time by 1 nanosecond. Ilara's eyes widened. A nanosecond? It is a billionth of a second. Aris said. It is indistinguishable from zero to a human. But to a computer, to a physicist, it is everything. If we can send a photon back 1 nanosecond, we prove the loop is possible. We break the barrier. We prove that cause can follow effect. He typed rapidly. I call it the Chronos Protocol. It is the culmination of 50 years of research. And tonight, Ilara, we aren't just going to simulate it. We are going to try it. The lab fell silent. The air seemed to thicken. This was no longer a lecture. This was an experiment. Are you ready? Aris asked, his hand hovering over the execute key. If this works, The photon will arrive at the detector before it leaves the emitter. For 1/1000th of a second, the universe will be broken. Elara looked at the complex array of lasers and mirrors. At the far end of the lab equipment she had assumed was just for calibration. She realized now it was the heart of the beast. "If we break the universe," she whispered, "will it notice?" "That," Aris said, "is what we are about to find out." Aris's finger descended, pressing the execute key with a soft click that sounded like a gunshot in the silent laboratory. There were no sparks. There was no thunder. The fabric of reality did not tear open with a scream. Instead, a small green laser on the far bench pulsed once a blink, so fast the human eye almost missed it. A cooling fan whirred to life for a moment, then settled back into a low hum. Elara stared at the monitor, her breath held tight in her chest. The screen displayed a simple graph, a horizontal line representing time and a vertical spike representing the detection of the photon. "Look at the timestamp," Aris whispered, his voice trembling slightly. Elara leaned in. The emission time, the moment the laser fired, was marked at exactly 12 hours, 0 minutes and 0 seconds. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. But the detection time, the moment the sensor on the other side of the loop received the light, was marked at 12 hours, 0 minutes and 0 seconds. 0, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. It arrived. Elara breathed, the realization crashing over her. It arrived before it left. By 1 nanosecond, Aris confirmed, wiping a bead of sweat from his forehead. The photon entered the microloop, traversed a tiny twist in the geometry of the circuit, and hit the target 1/1000th of a second before the trigger was pulled. We have just observed an effect preceding its cause. Elara looked from the screen to the laser array. It looked so ordinary, just metal, glass, and wire. Yet, inside that box, the ironclad rule of the universe, that the past dictates the future, had been suspended. "We didn't destroy the universe," she noted, looking around the room. "The chronology, protection, conjecture didn't vaporize us." "Because it was just a photon," Aris said, relaxing his posture. "And it was just a nanosecond. Perhaps the universe tolerates small infractions. Just as the police might ignore a car going kilometer over the speed limit, the laws of physics might allow tiny loops in time. It is only when you try to send a human or a message that could change history that the hammer comes down." He walked over to the window, gazing out at the campus lights below. "But we have done it, Elara. We have proven that the geometry exists. The rest is just engineering." Elara joined him at the window. The journey they had taken through the theories felt overwhelming. "It started with a limerick," she said, smiling. "Miss Bright." We laughed at her. "And now we know she was a pioneer." Aris chuckled. "We have walked a long road tonight. We started with Van Stockham and his spinning cylinders in 1937, realizing that rotation can drag space into a time loop. We moved to Kurt Gödel, who showed us that a rotating universe is is a time machine. We visited the black holes, the monsters of gravity that slow time to a halt, and the wormholes, Elara added. The tunnels through the apple. We learned that to keep them open, we need exotic matter. We need negative energy to push back the crushing weight of space. Quote, "We faced the paradoxes," Aris continued, "the grandfather who must not die." End of chapter 4. The party that no one attended. We learned that perhaps history is immutable, a fixed block where we are just actors reciting lines. Or perhaps the universe splits, and every time trip creates a new world. "And we looked at the end," Elara said softly. "The escape hatch, the way to outrun the death of the universe itself." Aris turned back to the room, looking at the equipment with a sense of finality. We have the map. We know the terrain. But will we ever make the journey? Will a human ever stand in a machine like the one in Contact and drop into the throat of a wormhole? What do you think, Professor? Harris took off his glasses and cleaned them one last time. I think the energy requirements are discouraging. The mass of Jupiter to hold open a door, it seems impossible. But, he paused, holding his glasses up to the light. In 1800, the idea of flying to the moon was impossible. In 1900, the idea of splitting the atom was impossible. Impossible is a word scientists use to describe things we haven't figured out how to pay for yet. He put his glasses back on. Maybe we won't build it. Maybe our grandchildren won't. But somewhere, out there among the billions of stars, perhaps a Type 3 civilization already has. Perhaps the network is already there, waiting for us to figure out how to dial in. John. Elara looked at the monitor again, where the graph still showed the impossible spike, the evidence of the broken timeline. It changes everything, she said, even if we never build a big one. Just knowing it's possible, it changes how I look at the now. It makes the present feel less solid. That is the gift of physics, Harris said warmly. It peels back the curtain. It shows us that the world is stranger and more wonderful than our senses tell us. We think time is a river flowing one way, but tonight we saw that it is an ocean. We can sail against the current, if only for a nanosecond. He powered down the laser. The hum died away. The lab returned to its dormant state, a quiet cathedral of science. So, what is the next step? Elara asked. Do we publish? Do we announce that we broke time? We check the data, Aris said, the cautious scientist returning. We run the test again, and again, and 1,000 times more. We look for the error. We look for the loose cable, and only when we are absolutely certain that we haven't fooled ourselves, then we tell the world. He picked up his coat from the chair. But that is work for tomorrow. For now, let us appreciate the moment. We are the only two people on Earth who know that yesterday is not quite as unreachable as it seems. Elara grabbed her bag. As they walked towards the heavy steel doors of the lab, she stopped and looked back at the darkness. Somewhere in the equations, somewhere in the geometry of curved space, the door was open. Miss Bright was still traveling. "Professor," she said. "Yes, Elara? If you could go back?" she asked, posing the question that had hung over them all night. "If we had the machine, and it worked, and you could go back to any time, where would you go?" Aris stood in the doorway, the hall light framing his silhouette. He thought for a long moment he didn't speak of saving the world or witnessing great battles. "I would go to 1915, he said softly. "Berlin. I would go to Einstein's study. I would wait until he put down his pen, just after he finished writing the field equations of general relativity. And what would you say to him?" "I wouldn't say anything," Aris smiled. "I would just shake his hand. And I would tell him, 'You were right. It curves.'" He opened the door. "Come, it is late. Or early, depending on your reference frame." Elara followed him out. The door clicked shut behind them, sealing the secrets of the Chronos protocol inside. They walked down the corridor, their footsteps echoing in the empty building, moving steadily forward into the future, 1 second per second, just like everyone else. But as they walked, Elara looked up. Through the skylight of the atrium, she could see the stars. They were points of light from the distant past, ghosts of ancient fires reaching them across the void. She realized then that she didn't need a machine to see history. She was looking at it. The universe itself was a time machine, and she was just beginning to learn how to read the dials. The journey was far from over. In fact, she realized with a thrill of anticipation it had only just begun.